Hi Year 12s, this is Mr. Lim here, and this is our first video on our equilibrium series. Right, there'll be 5 videos in the series. Actually, there might be 6, I'm not sure. And then we're going to be starting on with equilibrium systems. Right, today we're also going to be looking at open and closed systems, forward and reverse reactions, changes of rates of reaction over time, dynamic equilibrium, and then chemical and physical dynamic equilibriums. All right, so open and closed systems. So in equilibrium, we need to be talking about closed systems, but we have to talk about what they actually are. An open system is where energy and matter can enter and leave the system. So for example, that would be something like an open beaker of water. So when the water evaporates, the water leaves the system and it doesn't come back, right? So the water flies off and it's no longer there, right? So when matter can leave the system or enter the system as well, right? So that's an open system. All right, a closed system is where only energy and not matter can enter and leave the system. Okay, so a closed system would be if you put a cap on that beaker, and now we have, and now we have a closed beaker full of water. If evaporation occurs, it's going to be trapped in here. So you're going to have lots of little water particles of water vapor stuck inside that system, and they can't get out. All right, so that's an open and a closed system. You might want to write down those definitions. Okay, so we all know that for a successful reaction, all you need is a collision, correct orientation, and sufficient energy. All right, and that's to go from substance A to substance B. All right, so however, you've got to start thinking about, if I have B to go to A, what do I need for that? All I need are the same 3 requirements for a collision. For a successful collision, I need the collision, I need the correct orientation, and I need sufficient energy. Now, 2 of those things, the correct orientation and sufficient energy, will be different from A to B as B to A. But effectively, the reverse reaction can occur within the right conditions. So let's say, take example, the reaction of propane plus oxygen going to carbon dioxide and water. Okay, all right, so that's a combustion reaction. Do we think that is exothermic or endothermic? It's going to be exothermic, and we should remember that exothermic reactions look like that. Okay, so exothermic reactions, remember this is enthalpy, this is progress. Right, so you've got this reaction which is going and
Hi, Mr. Lim.
shown there. Hi, Mr. Custodio again. Right, so here you've got what? The activation energy, and here is the change in enthalpy. Okay, so for the reverse reaction, you want products to go to reactants. So what's the reverse reaction? It's effectively, the activation energy for the reverse reaction is effectively this, where you've got the amount of energy to go from products to the transition state and then back. What's the change in enthalpy for the reverse reaction? It's actually the same. Change in enthalpy there. All right. So the amount of sufficient energy from A to B to A for this particular reaction is very different. All right. And if you're thinking about the correct orientation as well, for this one you need 1 propane, 5 oxygens to reactivate, and those 5 oxygens got to crash into the propane. And the carbon dioxide, you're going to have 3 carbon dioxides and 4 waters. Right? This particular collision is much more likely to occur than this collision with the correct orientation. So this correct orientation is quite easy. This correct orientation is quite hard. Right? So that's why you may not have lots of the reverse reaction for this particular reaction. Right? Mainly because you need a lot of energy and you need a very, very unusual correct orientation for this one to occur. All right, so that is the forward and reverse reactions. They can occur and they have different correct orientations and sufficient energies, but they can occur under the right conditions. All right, so let's have a think about what that means then. So if we think about a reaction, as it progresses, there are less reactants, saying that we started off with a whole bunch of reactants and we're going and turning them into products. If there are less reactants, over time there are less collisions. Over time there are less successful collisions, and over time there will be a lower forward rate of reaction. You can show this graphically, right? You have time and rate of reaction. Okay, so the rate of reaction starts off quite high, but then gets lower, 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 lower. All right, and it always comes to this curve, and I was trying to go for 0 there, but that's where it should be. Okay, the rate of reaction can eventually get to 0. All right, this is the first concept that we need to know, that the rate of reaction will change over time, and for the forward reaction, in general, as you start with reactants, it's going to get slower and slower and slower. Conversely, as the reaction progresses, there are more products. More products means more collisions, means more successful collisions, which means that there's going to be a higher rate of reaction for the reverse reaction. And if you were to show that graphically, that with rate of reaction here and time, you would see that that would go up. Okay? So, here's a question. If the reverse rate of reaction is going down, if the forward rate of reaction is going down and the reverse rate of reaction goes up, so that's the forward rate of reaction goes down and the reverse rate of reaction goes up, at some point in time they're going to become equal. All right? And when they become equal, that means that you're going to have equal amounts of forward reaction occurring as you do reverse reactions occurring. And if you have the same number of forward and reverse reactions, are you going to actually have a change in the number of particles of, say, reactants or products? Well, the idea is that if you're going at the same speed forwards and backwards, effectively you're not going anywhere, and so therefore you're actually going to have no changes in the amount of substance that there is over time. So this is what we call dynamic equilibrium, and you should probably write all of this down. If the forward rate of reaction decreases over time and the reverse rate of reaction increases over time, then there will be a time when the forward and reverse reaction rates are equal. At this point, the number of reactants particle used by the forward reaction, okay, so that's the amount that is consumed, and the amount that is produced by the reverse reaction are equal. Same for the product particles. Which means that the total number of reactants and products stays this constant over time. Which individual particles are reactants and products can vary. So say you had 100 reactants and 100 products and 20, you just go write that down. You had 100 reactants and 100 products, and there was a change of 20 in the reverse every second, and 20 every second for the forward, you would end up with 100 at the next second. However, out of those 100, right, 80 would be from reactants, or were reactants initially in the last second, and 20 would have been products previously, but they were just changed into reactants again. So that's what I mean by saying which individual particles of reactants and products can vary. Right? So given enough time, and if they're randomly selected, those 100, all of them would cycle through and be a reactant or a product at a given point in time. However, there would always be 100 reactants and 100 products over that time. That is dynamic equilibrium. All right, so let's use a bit more of a concrete example. Let's talk about stream classes here at Frame. So let's say you have Math 1 and you have Math 2. Okay, so you want to be moving kids forwards and backwards from these classes, right? So say you have 30 kids in the Maths 1 class and 30 kids in the Maths 2 class, right? Say, because we want the Maths 1 class to be the biggest as possible and the Maths 2 class to be the smallest as possible so that we can help them better, all right? Say every second we move the bottom 5%, and every second we move the top 10%. Right? So it's a little bit hard to move this because this one will be 1.5 people, and this one will be 3 people. Right? So after, we'll just go round that down to 2, because that will just be easier. Right? There is a net gain of 1 person in this class, 31, 29. Right? This would continue until, so this would change. The bottom 5% of this would be 1.6 or something. And the top 10% of this would be, again, 2.9, which would round to 3. Right? And so you would have another net gain here, 32, 28. Okay? But you see this number got bigger. This number here got bigger. This number here got smaller. Right? Eventually, this would get smaller and smaller, bigger and bigger and bigger, and this would get smaller and smaller and smaller until they were equal numbers. When they are equal numbers, then they'll be transferring back and forth the same amount of kids, right? They might be different kids, but they're going to be always have the same number, not as each other, but same number over time of kids. Let's talk about condensation and evaporation, which is a physical change dynamic equilibrium. Okay, so if I left a beaker out in the sun, after a day or 2, it might run out of water. All the water disappears. Okay, and then it's not there anymore. However, if I left a bottle of water out in the sun, the amount of water that was there would not change over many, many days. Why is that? Because this is a what type of system? This is a closed system, and this is an open system. Okay? Effectively, what's happening is that things are evaporating here, and things are condensing here. Right? When I first put this in the sun, all right, let's just talk about water liquid and water vapor. Let's just say that there is 100 water liquid particles and there are 0 water vapor particles. All right. So effectively, can there be any condensation if there is no 0 water vapor particles? There can't be. So what you've got is all of it, the evaporation, let's say there's 20 let's make this 1,000 to make it a bit better. 20 units evaporate, and there's no condensation because there's none there. All right, this goes down then to 980, and this goes to 20. Let's just say another 20 evaporate, and 1 condenses. All right. Then again, maybe you only have 960. No, wait. How many will I have? Won't be 960. It'll be 961. Why wouldn't there be 961? Because even though I lost 20, I've gained 1 extra. And this will be 39. All right. Again, this can occur again, 20, and then this will be 2. All right. So this will now be 9. Oops, that would be 20. This will be 9. How much? 943. Yeah, 943. And this will be plus 18, so that's just under 60, so 57. All right. Okay. So this would continue until the amount evaporating would equal the amount condensing. And then you would have equal numbers of water liquid or water vapor over time. Okay, remember the time scale is this way, time. Okay. Same thing can be considered for saturated solutions. Saturated solutions. Okay. You've got some at the bottom here. Some of it is dissolving. Some of it is crystallizing. Okay. And the rate of dissolving and rate of crystallization becomes equal when you're saturated, when you can't get any more. Right? Other systems like this weak acid here, ethanoic acid, you should remember that some of the acid turns into ethanoate and some of it turns into the H+. What type of theory of acid bases is this? This is Arrhenius theory. All right. So, as we go on, maybe what we'll have is we'll have 100 of these, and let's say only a small part of it turns into it. So let's just say 3. Okay. So then you have, after a little while, you have 97, and you'll have how many of these two things? You'll have 3 and 3. Okay. This will then become 2.9. Why is it 2.9? Because since I have less of these, I only have 97 of them, there's going to be less ionization occurring. All right. And that is going to be, going back might be 1. Right. So if I have 2.9 and 1, so we'll just round it to 3, so that'll be 5 and 5. Okay. Right. So let's say that now brings us down to 95. All right. Let's just say this is now 2.8, and this becomes 2. Right. So now we only have a difference of 1. Right. So you're going to have how many? 1. So you're going to have 6 and 6. Right. And you're going to have 90 something. Right. But eventually the rate of it going backwards and the rate of it going forward is going to equal, and therefore you're going to have that dynamic equilibrium. Right. You can show this as a rate of reaction graph, where the rate of forward reaction decreases and the rate of reverse reaction increases. And then eventually they'll be equal. And we'll be talking about more about graphing these types of graphs in the next video. Right. But that's the idea of dynamic equilibrium. Right. Where you have equal numbers going backwards and forwards. You've got a closed system, and you recognize that forward and reverse reactions are occurring simultaneously. All right, that's why we have this particular arrow, or this arrow, to show that it's a reversible reaction. All right, that's it. Ready for the next video.